All right, let's look at section 5.7. So let me go ahead and get into my slideshow here. So here we're doing derivatives that wind up being involving the natural logarithm rule. All right, so that's just that reminder that if you did the derivative of a natural log, that it would equal 1 over x. So that if you integrate 1 over x dx, see, it might look like you could do the power rule, but remember, if you switch that into the exponential notation, x to the -1, and you try to do it using the power rule, you would add 1, which would give you a 0 and give you a 0 on the bottom, and you can't do that. When that happens, that should remind you, oh yeah, this is the one that involves the natural log. And then a weird thing here is, then we would, when we do that, when we write the answer, we could say that we need to say the natural log of the absolute value of x plus c, because it turns out you can do that. And by doing that, you're enabling more input values, more values of x in there. Okay. All right, let's go ahead and take a look at the 3 questions that they suggest you look at. So on number 5, all that one really takes is you recognizing it as an ln problem, as really seeing that 1 over x there. So sometimes a little rewrite step can help. So when you integrate, the constant can just be carried along, and then you're kind of looking at this piece and saying, oh yeah, I can't use the power rule for the reasons I just mentioned. So that's, oh yeah, that's natural log, and I'll do the natural log of x, and then natural log of the absolute value of x, and then add c and be done. And you can use pattern recognition on these. I'll do this one using pattern recognition, and then I'll do it using the u substitution in case you're more comfortable with the u substitution. When I see that this denominator is just to the first power like it is, and there's no other stuff, no other x's there, I'm pondering that and thinking, hey, this is going to be a natural log type problem because that denominator is just to the first power. So it's like I have the 2x plus 5 in parentheses to a -1, right? So I have this situation right here. So if I notice that, I can go ahead and think, okay, I know that's coming, that 1 over 2x plus 5 is coming from the natural log of the absolute value of 2x plus 5. But then do you remember how if you did the derivative, how you would get a 2 for the derivative of the inside? So you're going to need a 1/2 to counteract that, and then throw in the plus c, and there you have it. Okay. Now, you might be more comfortable, though, having that set process. So what you could do is just let u equal 2x plus 5 and do the derivative of it with respect to x and write it in differential form. And then when you're looking at things, notice that there's a dx there. So you need the dx by itself. So that would be 1/2 du. And then you could rewrite the problem as the integral of 1 over u with 1/2 du. I'm going to put the 1/2 in front and the du there. It's all times, so it really doesn't matter the order I put them in. Then when I go to do the integral, I'm going to have the 1/2 with the natural log of u plus c, and I'll just replace the ln with 2x plus 5, and there you have it. Same thing we got when we used pattern recognition. All right, it might be a tad harder to see it, but on number 9, you could use pattern recognition because the derivative of the denominator would be 2x, and there you have an x. So all you'd have to do is counteract the effect of the 2 by multiplying by 1/2. Okay, let's go ahead and just do this one using u substitution. So for number 9, I would let u be x squared minus 3. And again, it's that denominator down there being to the first power that makes me think to do this. Then du would be 2x dx. Okay, so over here, okay, you see how that original problem, there's my x times my dx right there. So I need this. So I'm going to get the 1/2, do the 1/2 on both sides to get that by itself. Then I can replace this with u. I can think of it as 1 over u, and the x dx I can replace with 1/2 du. So I'll put the 1/2 here and the du there. All right, did you follow that? So the x dx is being replaced with 1/2 du. I'm just writing the constant out in front and the du at the end. The 1 over u came from the x squared minus 3 in the denominator. So it's really turning out to be exactly the same as this right here. So when we integrate, we're going to get the natural log of u plus c with that 1/2 in front. And then when we replace it with the u was x squared minus 3. Okay. If that had been x squared plus 3, I could take the absolute value symbols off because I know that would always be positive. With the minus 3, I need to keep them on there since x could be something like a 0 or a 1, and then I'd have a domain issue. All right, so that's it for this kind. And these are when you're trying to integrate rational functions that have like a 1 as the exponent of the quantity in the denominator. Okay, so the degree of this denominator is 2, but x squared minus 3 is only to the first power. That's what makes me jump and think about using the logarithm rule. Okay,